These words by Archimedes perfectly capture what we are about to explore. Today, we dive into one of the most fundamental rhythms of the universe, simple harmonic motion. The home-seeking force. Let's start with what I like to call the home-seeking force. Imagine a mass, m, attached to a spring. When we displace it from its equilibrium position, where x equals 0, a restoring force immediately tries to pull it back home. This is Hooke's law. Mathematically, we write it as, force equals negative k times x. That negative sign is crucial, it tells us the force is always opposite to the displacement. The constant, k, represents the stiffness. A high K means a very stiff spring that fights back hard. Now, let's look at the physics behind the movement. According to Newton's second law, the net force is mass times acceleration. Since the only force acting here is our restoring force, we can set negative k times x equal to mass times the second derivative of x with respect to time. By rearranging this, we get the fundamental differential equation for simple harmonic motion, the second derivative of x plus k over m times x equals 0. To simplify this, we let omega squared equal k over m. This gives us our final form, the second derivative of x plus omega squared times x equals 0. The solution to this equation describes the position of the mass at any time, t, usually written as x of t equals a times cosine of omega t plus phi. Now, if you want me to make a video specifically on differential equations and how to solve them from scratch, let me know in the comments. Sometimes, the best way to understand linear motion is to look at a circle. Simple harmonic motion is actually just a shadow of uniform circular motion. Imagine a point moving around a circle of radius, with a constant angular velocity, omega. If you track only the horizontal projection, the shadow it casts on the x-axis, you'll find it follows the exact same cosine path we just derived. The angle, theta, is simply omega times t. As the point rotates, the x-component oscillates back and forth. This is why we use sine and cosine functions, they are the natural language of cycles. Whether we look at the horizontal x position or the vertical y position, we see the same harmonic behavior, just shifted in phase. But SHM isn't just for springs. Look at a simple pendulum. When we pull a mass m back by an angle theta, gravity provides a restoring torque. Using rotational dynamics, we find that the torque equals negative L times m times g times sine of theta. However, there's a catch, this is only simple harmonic motion if we stay in the small angle regime. If theta is small, sine of theta is approximately equal to theta itself. Under this approximation, the pendulum mimics the spring, with an angular frequency, omega, equal to the square root of g over L. Finally, let's look at the energy. In an ideal SHM system, energy is never lost, it only changes form. At the maximum displacement, or amplitude, the mass stops for a split second, and all the energy is stored as potential energy, 1/2 k times x squared. As it rushes back through the center, that potential energy is converted entirely into kinetic energy, 1/2 m times v squared. The total energy, the sum of kinetic and potential, remains a constant horizontal line. It is a beautiful, eternal dance between position and pace.